Okay, so we're back now, and um, I've revealed the CA1 pyramidal hippocampal neurons. So you've got the dentate gyrus, which feeds via its mossy connections to the CA3 hippocampal neurons. They have their recurrent connections, and they also then project via axons called the Schaefer collaterals, named after Schaefer, to the CA1 hippocampal cells, which via the subiculum and entorhinal cortex connect back up to the cortex. So it should mean now that not only should we see that these two neurons at the bottom here with the CA3 neurons that represent hiccup and felid, we should also now see that after a couple of iterations of the hippocampus operating, that when the neural network comes to rest, a bit like the animal sleeping, the hiccup neuron and the felid neuron should reactivate and fire together as to create a situation in which they could increase the synaptic weight of the connection between the two, such that these two neurons fire together and they wire. It creates the environment in which they can wire together because of the increased calcium getting into the felid neuron, which would activate calcium calmodulin kinase 2, which will activate the nucleus, the DNA in the nucleus that would code for the AMPA receptor for glutamate, and thus increase the synaptic weight between the two. So let's give it a go. Hiccup alarm call, and I'll closely follow it up by felid down here. They fire together, and we go back up to the cortex. Those are firing together and wiring together. CA1 hippocampal neurons are firing, respectively, and they're feeding back up to the cortex. If we go up to the cortex, you notice that the hiccup alarm call is firing, and the felid alarm call, so the felid representation is highly attenuated. And that creates the conditions under which this would you would increase the synaptic connection, the strength of the connection between the two. And so effectively the neural network Capuchi-Net has learned an association between hiccup alarm call and its referent, which is felid. And obviously it's activating the predator escape response. But I wouldn't be too surprised, because if this is the equivalent of the animal dreaming and consolidating what it's learned from its experiences during the day, then you would kind of expect, well, I don't know if anyone else has got dogs or cats. I've got cats, and they tend to move their legs in their sleep, and I wonder if it's because they're responding to these learned connections in their sleep. So I'm going to reset the dynamics, and we're going to demonstrate that if we just press hiccup alarm call, if we remove the connection, the weighted connection that it's just learned, so I'm going to delete it now. We'd expect that if we just press hiccup alone, it shouldn't attenuate this hippocampus, because it's a signal by itself. And there we had it. You know, nothing, absolutely nothing learned. So that's fair enough for hiccup alarm call meaning felid. But how do we explain that capuchins have learned that whilst its hiccup alarm call could mean a predator, what about at feeding platform context, where we have a feeding platform? How does the Capuchin recognize, and this is the key to learning pragmatics in Capuchi-Net, and perhaps a key to how pragmatics have evolved in primates. We've got to show how the hippocampus system enables several contextual environmental factors to be linked towards how a signal can be interpreted at the semantic level. So we're going to move on to that now.